Today we are starting a new chapter, chapter 5, about the relationship between Heaps and graph theory. Is this working? Oh, wait. So this is the first part of chapter 5. So wait. There is a technical problem with my... Okay. The relationship between Heaps and algebraic graph theory.
Chapter 4.
So this class is dedicated to my dear friend, Jean-Pierre Muller, who each year he spends 6 months in France and 6 months in India. And in India, always we have, before starting any discussion, we have an aperitif. So in guise of aperitif, here is starting amazing fact about graph and heaps of pieces. So to any graph, you can associate a heap monoid. V is the vertices of the graph, E the set of edges. And the graph, we call this before the dependency graph. So the dependency relation is a relation related to the edge. The basic piece are the vertices. And here is certain visualization of a heap of pieces over the graph G. So I start with a definition. A neighborly heap. So I will take the second definition of heap. So in terms of graph and poset, you have a poset with a projection on the underlying graph with some condition. So in terms of graph and poset, you know the pi is a projection. Then the condition star is that for any pair AB in the heap, such that the projection of A equal the projection of B, so they are just the same, what I call a fiber. Then there exist two pieces C and D in the heap, such that C is between A and B, D is between A and B, and the projection of C and D are neighbor of P of I and P of B. Here is a picture. So you take, for any pair of A and B which have the same projection on this vertex, in the poset underlying the heap, there is two other pieces, C and D, such that the projection, you see, are connected by an edge to the projection of A. So these pieces are in competition, they are in dependency.
So the graph is the graph of concurrency relation?
Yes, the graph is a graph of concurrency relation. You see? The dependency relation is defined by the edge of the graph. So two vertex, which are the basic piece, the vertex, two vertex are dependent if and only if they are connected by an edge. So the basic piece are the vertex of the graph. Here, this ball are the basic piece of the heap. I denote the heap over a graph by this notation. The dependency relation is just any binary relation gives you a graph.
And also, as in you have 1 and 2, so they are.
I put the level here, but when the number, the level, but
the rightmost here, yeah, these two they project to the same, but
yes,
there need not be a loop, but still they are dependent.
They are dependent. Yes, yes. The graph has no loops, and a letter doesn't commute with itself. A letter is dependent of itself. Think of the heaps of subset. It's the worst case where the two subsets are exactly the same. If they intersect, one is over another, but if they are the same, then it's a worst case, one is over another. So in the same, what I call fiber over a vertex, that can be many, many, many pieces of the heap. But the condition, you see, is that if you have two pieces which project on the same piece. Between them, in the poset of the heap, I can find two other pieces such that the projection are in dependency relation with the projection of the two pieces.
So otherwise it will collapse.
Yeah. Otherwise, there is somebody between the two, there is somebody which block the fact that you cannot join the two pieces one over another. So these two other pieces, maybe they are the same. Maybe they are different.
But isn't this like putting a counter group, saying that if you have two pieces of the same with the same projection, then they cancel?
Yes, it's no, it's not. No. This will be strict heap. No, they don't cancel. It's usually the general condition here. I don't say that if I take two pieces one over another, they will cancel. We will do this when we will work with the symmetry group or the temporally Lieb algebra. Then two pieces cannot be in touch. I will call this strict heap. Strict heap means that you cannot have inside the heap two pieces which are just one over another. It means the equivalence class of word, you cannot put the two letters, cannot be put together. The same letter cannot be put consecutive letters. This is strict heap.
But
So,
the number of heaps is the same as the number of elements in the counter group.
no, but the number of elements. Well, this will be another discussion. Okay, so definition. A Neburle heap, it's a heap satisfying this star condition. You see, between any two elements in red, there is always blocking between the two blue, at least two elements C and D, such that in the poset of the heap, C is between A and B, D is between A and B, and the projection are neighbor of this.
Is it strict inequality also?
No,
A less than C.
well, it's strict, yes. It cannot be the same. It's two different pieces.
And C and D are different as well.
Attends.
C is not equal to D is also part of it.
No, in the poset, they are not the same. C and D, they are not the same. So C and D are neighbor, you see. They are in two different positions. And in the poset, of course, A is strictly, C is above A, B is above C, B is above D, D is above A. Is it okay for this definition? You can always find between two NA pieces projecting on the same vertex of the graph, you can always find two other pieces which are blocking in a certain way these two pieces one over another.
Why do you need two?
That's the definition. It's enjoy your aperitif. It's just it's an appetizer for the just to entertainment. Before any discussion with Jean-Pierre, we have always a good aperitif, and then we can discuss seriously. So, okay. So the second definition, a Neburle heap is called maximal. If and only if it's maximal, you cannot extend the heap by addition of a piece in any position to get a larger Neburle heap. You cannot, if you add a new piece anywhere, inside, above, below, inside, there will be a violation of the neighbor condition. I'll give you an example. So here is an example, is the skew-Ferrer diagram. A skew-Ferrer diagram which are rotated by 45 degrees. And you see, you replace each cell of the Ferrer by a dimers. And any poset, you remember, any poset can be viewed as a heaps of things. The poset of a Ferrer diagram or skew-Ferrer is a poset in the square lattice when you go following the row from left to right, following the column. So this poset, this skew-Ferrer is visualized by these heaps of dimers. I keep it floating in the air, these heaps of dimers, like a pre-heap. And you see this heap satisfies the condition, the neighborly condition. Between these two dimers, there is two other dimers. If you take any pair of dimers, like this one, there is only 3 pairs, this one and this one, there is always 2.
You can add one. You can add one on top.
Yes. Okay, here it is. And what else you can do? Where? Here? Okay, below. Okay, you can add. You see easily that it's not a maximal neighborly heap. You can always add many. In fact, if you like the heap, okay, if the gravity fall down, everybody fall down like this. So, sorry, it's a long aperitif. Third definition, a neighborly heap is called two neighborly. It's a special case of neighborly heap. If there are exactly 2 occurrences of pieces C and D in the condition of the beginning. Beginning condition star, but there is at least 2 pieces. Now there is only 2. 2 and only 2. Then comes the amazing fact. Wildeberg, he lived in Sydney, 2001. Let G be a graph where there exists a maximal neighborly heap. Suppose a graph has a maximal neighborly heap, and suppose that moreover, this maximal neighborly heap is 2 neighborly. It is a maximal neighborly heap, and in fact, this maximal heap, maybe there is several maximal heap, but this maximal heap is 2 neighborly.
You didn't give an example of a maximal neighborhood.
No.
Now he's going to give us
Now I am going to give an example of this. Then G, the graph is one of the following graph. If you have this condition, with the 3 definition, the graph is this AN, or DN, or E6, or E7. That's all.
not even E8.
I will discuss this later after. And then the number of such heap, for AN there is n heaps, for DN 3, E6 2, E7 1, E8 is 0. So there is no such heaps for E8. Here are the heaps. So for AN, you see this is a skew Ferrer, but this is Ferrer diagram which are a square. And there is n possible way to do these heaps on the Dynkin diagram A5. Now D5, there is 3 different heaps. So there is this heap, it's like a triangle. You see the notation is I take the second definition. You have a heap with, this is the assay diagram of the heap, and each vertex is labeled by one of the vertex of the underlying graph. See, so vertically this go to 4. So all the vertex you go 1, 2, 3, 4, 5. It's the same as here. 1, 2, 3, 4, 5. It project on this segment line. But here's the difference. So they're all project, but there is a 0, the special vertex 0. So here you make a triangle with 1, 2, 3, 4, 5, and you alternate the 0 and the 1. So this can be as big as possible. This makes 2 heap, and the third heap, just a little square here, and then a long chain here, a long chain here. So this is the 3 heaps for D5. E6, there is 1 heap. The second one, when you just reverse, takes the complementary. And E7 is this beautiful heap for E7 that Wildeberger calls it a swallow. This is a beautiful heap. There's only 1 for E7.
So for AN, is it just all the
That's
Ferrer diagram?
for AN, there's all the Ferrer diagram, but which are a square. Because
No, not the maximum one. All the neighborly.
all the neighborly, yes, probably. Not the maximal.
Two neighborly. Two neighborly is the same as Ferrer diagram.
Can you give the statement of the proposition again?
These are the maximal neighborly.
Mhm.
Two neighborly.
Let J be a graph for which there exists a maximal neighborly heap. There exists one. And which is too neighborly. So that's the only possible graph. So some complement. I am supposed to give a class to undergraduate students also, so they don't know about Lie algebra and Dedekind diagram. So for students, in fact, if the graph has a maximal neighborly heap, if there exists, then G is a tree. Exercise proves this. This is easy, very easy to prove that. If it's not a tree, then you can add already you get the solution. But it's less easy to show that the poset is a lattice, in fact. So this, oh, it's, yes, lattice means there is a meet and a join. In fact, it's that.
Because it's too neighborly.
When it's too neighborly, then it's a distributive lattice. When it's too neighborly, for this graph of this poset. But when there exists a maximal, which is not necessarily too neighborly, then the underlying graph is a tree and the poset is a lattice. So as a complement for expert in the field, this is exactly what Proctor called the irreducible minuscule poset. This corresponds to minuscule representation, and there is a second paper of Weilberger where he defines some raising and lowering operator in the ideal of the heap, which give a representation of the simple laced Lie algebra. And all simple laced Lie algebra have such minuscule representation, except for E8. So this is why this tableau is E8 equals 0. It's related to this representation. So this is deep. It should be. It's outside of the level of this class. This should be a second class, a whole course about. This is a book of Richard Green about combinatorics of minuscule representation, where he used also some operator on what he called full heap. It's this kind of idea also, full heap, where there is not too much hole in the heap. This idea and to have this condition star also is related to fully commutative element in Coxeter group. So there will be a chapter on fully commutative element in Coxeter group, only for the AN, for the symmetry group, for the most simple case. And so this is Richard Green, is all this team of students who have made a lot. They make thesis paper on this subject using Heaps for representation of a Kac-Moody algebra. And so there is a lot of combinatorics in representation theory, and Cambridge University Press publish many books on combinatorics of representation theory. So I think we are ready now to start this chapter after this amazing fact about relating. So you can say something on the graph just from the structure of the heap. It's some deep relation. So first generality about algebraic graph theory. So algebraic graph theory is trying to relate the combinatorial property of graph, to relate them to some algebraic object. So you can define some polynomial, some vector space, some power theory related to the graph. So this is the first book, very well-known classical book, was Algebraic Graph Theory by Biggs in 1974. And there is connection on this subject with statistical physics, knot theory, Lie algebra, Heaps theory, etc. So here I will introduce some in the Museum of Polynomial related to graph. There is some very classical polynomial, the characteristic polynomial related to a graph, which we have the adjacency matrix. We have already seen this, that the characteristic polynomial is the determinant of 1x minus a. So we will use this in this chapter, the characteristic polynomial, the fact that you have the roots are real number. So we have seen in chapter 2c, we have seen the matching polynomial of a graph. A matching is just a set of edges 2 by 2 disjoint, and we have associated a matching polynomial to this. It's a polynomial enumerating all possible matching. So this was done in chapter 2. I will come back in this chapter about matching polynomial. So there is a well-known also the number of perfect matching. It's a constant term in the matching polynomial. And this number of perfect matching is well known in physics as a coefficient of the determinant, because the Ising model in statistical mechanics for ferromagnetism, you are supposed to compute a big coefficient, or a big the number of perfect matching of certain planar graph. When the graph is planar, then you have a formula given by a coefficient. Then today we will especially go on the chromatic polynomial. Chromatic polynomial for any graph, you define this chromatic polynomial as a number of ways to color the graph with lambda color. A coloring means a proper coloring, means that two vertex does not have the same color. In fact, two vertex connected by an edge does not have the same color. And the chromatic numbers is the smallest number nu, such as that this gamma g of nu is different of 0. So it's a minimum number of color you get to color the graph. So this is strongly related to the 0 of this chromatic polynomial, because if 4 is a 0 of planar graph, this means that the 4-color conjecture is false. To be able to color any planar graph with 4 colors, 4 must not be a 0 of the... But the 4-color theorem is almost false. I mean by that physicists have defined a sequence of graph such that some 0 of this sequence of graph, at the limit, they tend to 4. At the limit, the 0 becomes 4. So it's very close. So in this class, we'll have also the number of acyclic orientation of a graph. So acyclic orientation means you put some orientation in the edges of the graph, such as that there is no cycle appearing in the graph. And we have already considered in the Wilson algorithm about loop erasing walk, we have considered spanning tree. A spanning tree is a trees formed by the edges of the graph, such as that any vertex of the graph belongs to one vertex of the tree. And there is a famous polynomial, the third polynomial. I will not define here, but the third polynomial is a polynomial with two variables, x and y, which is a summation over all possible spanning tree. So if you put x equal 1, y equal 1, you get the number of spanning tree. Sometimes it's called the complexity of the graph, the number of spanning trees. So there is two parameters, which I am not going to define, and this is a very beautiful polynomial. Many polynomials are deduced from this polynomial, and it's related in physics to the Potts model. So the value of this polynomial for one mond is the number of spanning tree, and the value for x equal 2, y equal 0 is the chromatic number. And in the second part of this chapter also, I will talk about the zeta function of a graph, which is an extension of the Riemann zeta function. And of course, all the relation here, we are going to see the relation between algebraic things and graph is the relation between the heaps you can build on the graph and the graph itself. So the main part of this class will be devoted to chromatic polynomial and acyclic orientation of a graph. So I have talked about the chromatic polynomial. I just recall the definition. It's the number of coloring of the graph. When I say coloring, it means proper coloring. Proper coloring means that two vertex connected by an edge does not have the same colors. And I denote by A of G the number of acyclic orientation of G. And N of G will be the number of vertices of the trees. And then I have a famous classical theorem by Stanley, more than 40 years ago, in 73. He said that the number of acyclic orientation of the graph is up to the sign. It's the value of the chromatic polynomial for lambda equal -1. So this is a nice theorem. See a cyclic orientation of the graph and coloring the graph. So I will prove this theorem using Heaps theory. So the idea come in fact from a long time ago by Gessel. Ira Gessel he proved this by using the commutation monoid, Cartier-Fota. So I will do everything in terms of Heaps and visualization to, I think it's maybe more clear to get this. And there is 4 main ideas. Yes? Chromatic polynomial? I defined it before in the general introduction. A chromatic polynomial for a graph is a number of ways of coloring the graph, a proper coloring, with lambda color.
When you put this -1, so first you have to prove it's a polynomial.
Well, -1 color means that this number of ways of coloring the graph with lambda color is a polynomial. It's a polynomial in lambda. So I can put the value lambda equal -1 in this polynomial. So, and then it makes sense to color the graph with -1 color. It's just a polynomial in lambda.
Is it obvious that it's a polynomial in lambda?
You will see during the proof that it's a polynomial. No, it's not. It's easy to prove that it's a polynomial.
Usually it's proved by induction.
No induction here.
You don't like induction.
No. Induction means you don't understand the problem. When two things are equal, you have to show that really to understand you can go from one thing to another thing. If you make by induction means you are going to verify. No, don't verify. We must prove. Prove means that you understand why they are equal. No induction here. Please. So it's a conceptual proof, you see. So this proof is combining 4 different ideas, which are simple. So it's 4 ideas which I will go. These 4 ideas are simple, and it gives the proof of the theorem of coloring with -1 color graph. So first idea, coloring a graph. When you color a graph, that gives you partition, the different colors, and each vertex with the same color is in fact what is called in graph theory independent set. And we love this because it's trivial heaps of pieces. So you have trivial heaps of pieces. Each vertex with the same color is a trivial heaps of pieces. And we are in a heap theory class, so we should make a heap of this. So each trivial heaps, I am going to make them as a heaps. So first, to transform this problem into the coloring into a heaps of trivial heaps. Second main idea, if you have a generating function of current object, then 1/1 minus f is a generating function of a sequence of object. Because here I have a sequence of trivial heaps. I am going to take the product of this sequence of trivial heaps to make a heap. And then, but a heap, there is a beautiful inversion lemma, which give me the generating function of heaps in terms of the inverse of the generating function of trivial heaps. And then there is another idea, which introduces a new definition, a multilinear heaps. So what means a multilinear heaps? It's a heaps such as that in each fiber over a vertex is all the pieces which project on V. You see here as a fiber, there is 2, here 2. So multilinear heaps means that in each fiber there is one and only one piece. So it means when you project the whole poset on the graph, each vertex appears one and only once. I call this multilinear because if you think in terms of words of commutation monoid, this is a multilinear word. Each word, every letter appears one and only one. So this idea number 4, give you, in fact, there is a bijection between multilinear heaps on G and acyclic orientation of G. So acyclic orientation becomes a heap.
This is not a multilinear.
No, this one, no. But the next one, yes. This is just to show what is a fiber. to show the definition, and here it's, so you see, in this fiber above it, there is only one ball. Here there is only one, but here there is two, here there is two, here there is no ball. So multilinear, there is two conditions. There is at least one ball. In each fiber there is one, and only one. So now I show you the bijection between multilinear heap and acyclic orientation of graph. So here is the bijection. You see, you take this acyclic orientation, and you say you lift, so this is going to be at level 0, and then you see there is an edge between A and B. So I have B must be above the D. You see there is an edge between D and E. So I put an edge, see it's going up in the poset underlying the heap. And this edges in dot point means you don't need, in fact. In fact, from D to C, see, there is an edge in the acyclic orientation, but this edge, you see, is a consequence of this and this. So in brown, in full line brown, I put the assay diagram of the heap. In dot line, this is the edges you don't need because it's a transitive closure of the order relation. So you have to think that this is a bijection between any multilinear. If you take a multilinear heap, then there is an underlying poset of the heap. There is no cycle in this poset. And if you project this poset on the graph, which means that each vertex of the poset is going to be sent on the vertex of the graph, and each edges of the assay diagram of the poset is going to be sent in an edges of the graph, which gives you the cyclic orientation. So the cyclic orientation, you see, is a transitive closure of the projection of the assay diagram of the poset. So here I put the level 0, 0, 1, 1, 2. So suppose there is lambda possible colors. Suppose that k of these colors are used. So I am going to define a total order on the colors to be able to lift, to transform my coloring of the graph on the flat level, at the sea level, to lift it above the sea level, and to have to go level 1, 2, 3, to go very high. So if you color, if you give an order in the color, C1, C2, Ck, then this gives you a sequence of trivial heaps, T1, T2, Tk. Each trivial heaps correspond to one of the colors. So I have a sequence of trivial heap, and I take the product of this sequence as a heap, product of heap. So I get a multilinear heap. But you have to give an order in the color. So for example here, the first color will be the blue. So I lift them at level 0, and I get the first trivial heap. I was at level -1 on the graph. Now I am at level 0. Now the second color is going to be the red one. So I lift them at level 2, you see, to get a second trivial heap. And then the green one gives you a third trivial heap. And so you get, see, you transform your coloring of the graph with the total order of the color, of the k color, which are chosen among lambda color, you get a multilinear heap. In fact, this idea of transforming the coloring into a kind of poset, in fact, it is in the paper of Stanley. The first page of the historical paper of Stanley, the chromatic polynomial, he gives this interpretation as a number of pair sigma A, where sigma is a map from the vertices of the graph to 1, 2 until lambda. Lambda is the total number of colors. And A is an orientation of the edges of G such that this orientation is acyclic. And if an edge is connected between U and V are connected by an edge in the orientation, A, then the sigma must be compatible with the order of the color. So it's implicit. It's kind of implicitly this idea of a heap, putting the color instead of staying at the flat level is much more beautiful to go in 3D, and you have more. It's more easy to give the proof and to have the intuition of the spatial power of the heap. So let's give some definition to state really how to prove it's a polynomial. And this proof is equivalent to all the classic proof to show it's a polynomial, because people take a partition, it's another partition of a color, and then you put. But this is the same kind of proof, but just by using the level of each layer, it's a color, and there is a total order on the color. So I will take a heap, I will define a layer factorization of F. It's a way of decomposing your heaps into trivial heaps. Maybe there is different way. The same heaps can be decomposed into. So layer factorization, the sequence T1, T2, Tk, it's a sequence of k trivial heaps, such that the heaps is a product of all these trivial heaps. So the number of layers is at most the number of elements of the heap. If you take each vertex to be a single layer, then you can decompose your heap into a product of n layer if the heap has n elements. But in general, see, there is different way to factorize a heap like this. Not exactly, no. Cartier-Fourier normal form is the layer is you take all pieces at level 0, all pieces at level 1, all pieces at level 2. So here is different. Because some pieces that, you see, there is different decomposition. For example, it's the decomposition. Sorry, for example, if you take each single piece to be a layer, so you can have a decomposition into any heap is a product of the any heaps with n elements can be written as a product of n heaps reduced to one piece. So each layer can be reduced to one element. So you have a number of layers is n. So it has nothing to do with the normal form.
But if you take the minimal case, that would be
not necessarily, because suppose I have one of the person. Suppose I have two layers in the Cartier normal form. Suppose I have an element at the floor which can go up at the first level without hitting anybody at the first level. You can lift a piece if it does not been dependent of. So you can lift a piece if possible to. So it's you have more generality than the Cartier-Fourier normal form. So I will denote by, for a heap F, beta k, the number of layer factorization of F. For any heaps, you have a certain number of ways to decompose your heap as a layer. So the maximum number of layers is n, and the minimum, you can find it in the Cartier-Fourier normal form. So now I am going to put some colors, because my layers, they come from the coloring of the graph. So let's define a color layered heap. It's a layer heap, so there is a sequence of trivial heaps, such that each layer is color. Coloring a layer means that all the pieces of the same layer, Ti, have the same colors, but the condition is that all layers have all distinct colors. At each level, there is a different color. No level appears with the same color. Then everybody in the same layer, in the same level, have the same color. And so I can say easily that if lambda is the number of possible colors, the number of color layers associated to the heap F is this. Right? The number of ways, for each heap, the number of ways to decompose the heap into k layers. The first layer, it's a totally ordered sequence. First layer, there is lambda choice. Second layer, lambda minus 1, etc. Layer k, lambda minus k plus 1. Now I am close to the chromatic polynomial. So now I have to define a heap is covering the graph. Heap is covering the graph. If any vertex is of the graph, the fiber above this vertex V is not empty. So for any vertex of the graph, pi minus 1 of V, all the vertex of the heap with project on V, this fiber is not empty. When you project the whole heap onto the graph, then some pieces, all the pieces, basic pieces are reached. There is all fibers, there is no fiber which are empty. And so a multilinear color layered heap is in bijection with an order coloring. So when you have take a coloring of the graph, take a total order of the coloring, what I have done before, then this is in bijection with a multilinear color layered heap. That's what we have done. We have done here, we have a coloring of the graph with 3 colors, and I have defined an order on the color, the first color, second color, third color. This gives me a heap. This is a multilinear heap, which is in bijection. So if you project all the ball down, then this gives you back the coloring. So if you totally ordered, I just repeat, if you totally order the color of the graph, then the number of coloring, the chromatic polynomial is going to be this. But you have to divide by something because you're ordering the color. So which means the following proposition. The chromatic polynomial is the sum over all multilinear heaps over G of beta of K of F multiplied by this polynomial, which is nothing but the binomial coefficient. So this gives you proof that the chromatic polynomial is a polynomial. In fact, it's the same analog proof when you have a classical proof in literature. You take a partition of your vertex into trivial heaps or into independent set, and then this partition you put an order. There is lambda way to color the first one, lambda minus one, etc. And so this is analog proof, but in terms of heaps, with this number I will use the number of ways to decompose the heap, because this is more powerful because I am taking all the heap. The special case of the Stanley theorem is only for multilinear heaps, where in each fiber there's only one color for each vertex. And so the proposition Stanley theorem becomes that if you replace lambda by minus 1, it means that this binomial coefficient for lambda equal minus 1 becomes minus 1 power k. So we get easily that the value of the chromatic polynomial for minus 1 is the sum over all multilinear heaps over F, over the graph G, sigma for each of this heap. You take this number way of decomposing the heap into layers, and minus 1 power k. So this leads to a definition which is more general than coloring. This is more because I'm working with general heap instead of working with multilinear heap. So we have a kind of multi-coloring of the graph. So you take a vector k, bold k in k1, k2, kn, if n is the number of vertices of the graph. And multicoloring, it's you give some color to the vertices of G. And in each vertex of the graph, I call the vertex of the graph 1, 2, n. In the vertex I, there is receive ki colors, so you can put many colors on the same vertex, but such that two adjacent vertices receive only disjoint colors. And you have a kind of extension of the chromatic polynomial, the multicoloring chromatic polynomial. So you have the graph G, you have k, this vector k1, k2, kn, and this is a number of multicoloring associated to k with lambda colors. And so what we have done before by putting our layer for any heap, not only multilinear heap, but any kind of heap, this gives you a bijection. If the multicoloring take an order on the color, and there is a bijection of ordered multicoloring with color layer heaps covering the graph G. with a special case. If it is multilinear, then you get, for the case 1, 1, 1, 1, 1, you get only one color per vertex. So here is an example of a multicolor layer heaps. So there is different layers. There is 4 layers. In each level, all its trivial heaps, having all vertex the same colors. And now if you take the projection of this heap, like this, so you see some vertex, they get 2 colors, but the condition coloring means that if the vertex have an edge between the two, then the color must be different. Here it's purple and red, and this is green and blue. So my friend Jean-Pierre Muller, he has done a lot of pictures in India. In India, it's a multicoloring country. This is wall from Jaipur in Rajasthan. So people are painting, repainting over another wall. So there is you see, the coloring problem when you put one color for each vertex. It's better to put several vertex. You color once, then you color a second time, a third time. Each generation color, you don't erase the color before. So this is the idea of heaps of colors. I am defining, in fact, heaps of color. I am going to define the chromatic power series of a heap. So it's amazing, this wall in India. This is picture of wall he took in Rajasthan, and he make an exhibition in Auroville. He loved to mix the science and art. He was photographer, freelance photographer, but he was also the director of the French Institute in Pondichéry, and in France also. He was a big director of a big institute in France, but he loved to mix science and art, and this is amazing picture. This looks like a piece of art. This is just wall inside you get in the house of in Rajasthan. You know. So see, you would have loved multicoloring of So let's go to multicoloring polynomial. So the beautiful paper, which is an extension, in fact, of the there's a beautiful paper, the chromatic polynomial by Venkatesh and Viswanath, which are here. It's and Arun Kumar, yes. No, beautiful paper about the relationship between chromatic polynomial and Kac-Moody algebra, and between multichromatic polynomial are related to the root multiplicity of the. This is an algebra extending Borchert algebra. I am not an expert on all these fields. I am impressed by coloring is very simple things, and multicoloring. You do this very often in India, and to be related to this deep algebraic structure, it's amazing, and that they give an interpretation of the multiplicity of the root in terms of this multichromatic polynomial. So it's a beautiful work to this relation, and so it's time to define behind all this. There is in fact the chromatic power series. Why not to take the sum of a whole heap covering G? So this is a generating function with lambda. You take exactly the same, but instead of restricting to multilinear heap, you take any heap. So you take like it's an infinite power series, which give you like a generating function for multichromatic polynomial. Multichromatic polynomial, you have to take inside the heap, you have to count how many pieces go to as a projection to vertex number I, vertex number j, vector. So if you take in each fiber, you give the number of vertices in each fiber of the heap, this gives you the multichromatic polynomial. So I can define the infinite series, what I like to call the chromatic power series of the graph. In which, so if you project the heaps, you have an interpretation. This is a class of heap with a degree k1, k2, kn in each of the fiber of above the graph.
What is beta k of f?
Beta k, it's a number of way, beta k?
Number of ways of coloring.
Number of way of decomposing a heap into a layer of a heap such that
K.
there's K layers, that's all.
And V of N.
Or I put a weight. This makes more beautiful. It's better to put a weight. When you take the infinite generating function, to be safe, put a weight. So they would put a weight V, and also they would put a weight V in the chromatic polynomial. It's like kind of a. In physics, many problems can be solved if you have just counting, but you put a weight and then variable, and then it's the same, but it's much more powerful to put a weight. So now, one of the main ideas also was we are taking sequence of trivial heap. So we know from the symbolic calculus that we teach at the first part of the class about the generating function. If you know the generating function of something, then 1 over 1 minus f is the generating function of sequence of things. So I am taking trivial heaps of pieces, and this is the generating function for sequence of trivial heaps of pieces. And then if I add a variable t is going to take account of the parameter number of element k in the sequence. So I can write this equality. This is the generating function for sequence of trivial heaps, and t is counting how many trivial heaps you get. So I can write this with put the weight, so I have this equality. It's very simple equality, sequence of heap. Now if I put t equal minus 1, this is what I have to do to get the value of chromatic polynomial for t equal minus 1. And it would be more beautiful for trivial heaps when I have the inverse of trivial heaps. For the inversion theorem 1 over d, it would be beautiful to have the alternating generating function of trivial heaps, to have some minus 1 inside. So let's do the chance evaluation v bar equal minus v alpha. So each basic piece, I put a minus. It's very easy. You just change the valuation, v bar equal minus v. And then this, put t equal minus 1, so it's going to give 1 plus, and 1 plus the new valuation, so you have 1 plus sigma over all trivial heaps of minus 1 power number of element of heap, v of t, v bar of t. Which now the inversion theorem, the inversion lemma give you this equal this. No, it's general. We are working with a general, I will get a more general theorem than the general, the restriction to multilinear. There is the first restriction, the heaps is covering the graph. Second restriction, the cover is a multilinear. Now I have v bar, so I just replace v bar by v, which give you this, by replacing the valuation. And so this is equal to this. By applying these two elementary lemma, sequence of things, and inversion lemma of the monoid. And just putting t minus 1 or changing the sign of the valuation, this right-hand side equals this. Okay? So I just rewrite this. I have a beautiful equality. The sum over all heap of the beta k, number of ways to decompose the heap into layers, with minus 1 power the number of layers, becomes this, where now it's minus 1 number of pieces. I think there exists a bijective proof of this, without forgetting everything I've done before. And there is involution for a good student who like involution, and not recurrent relation or... And so if I define, I have defined this chromatic power series by the sum over all heap covering G. So if I put lambda equal minus 1 in this generating function, I get exactly this. So the chromatic power series is equal to the sum over all heap of minus 1. Because Well, you have to. This is true for any. Think of this as a formal power series with the Heaps as like formal variable. Each species should be a formal variable. So if this is true, in general, this is true for Heaps covering the graph. If you put on both sides the conditions that the Heaps have covering the graph, this is again an identity which is true. And if I put a third condition to be multilinear, it's still true. So it's a restriction of this identity to some family of graph, becomes another identity, which is a projection of this very general identity. And so I get that the gamma for lambda equal -1, this value of the power series is going to be the sum over all this same summation, but now the Heaps is covering J. This is the definition of chromatic power series. I have to cover the graph. Every vertex must be colored by a color. I will get a multi-coloring. But now if you restrict this to multilinear, in each fiber there's only one vertex. So if I restrict to this subclass of Heaps, I get the same identity, but instead of the chromatic power series, I get the chromatic polynomial. So you can see the power of the thinking in terms of Heaps in general with a good weight, and then you deduce some more and more of if you want to go to multilinear chromatic polynomial, then you have to restrict the heap to have a certain number of pieces in each fiber. So you should get a formula for -1. I think in your paper you have an interpretation of this in the paper. So I will not continue too much on multichromatic. And so if I replace now in this the weight, I have some weighted chromatic polynomial, weighted chromatic power series. I have something more general. If I replace the weight to be 1 for each vertex, it makes sense. There is a finite number of vertex. So I get here the number of multilinear Heaps on G, which are, in fact, the number of acyclic orientation because they are in bijection. And that's the end of the proof. So see, we have make a detour through more general theorem with Heaps, and then we start from the coloring. We lift everybody at some level. We reason on the Heaps, and then we project everything. We go back to the ground level to go to the... So some exercise for maybe research exercise. So there is a theorem I did not know before preparing this class, a theorem in graph theory, which is called this theorem of all these people. It was supposed to be a conjecture of Berge in 1958, and so this theorem is the following: that these two conditions are equivalent. G, the graph G, has an acyclic orientation in which the longest path has at most k vertices. There exists an acyclic orientation with the longest path at most k vertices. Second condition, G can be colored with at most k colors. So you are connecting the way of coloring a graph with the way of finding a longest path in an acyclic orientation of the graph.
Both are related.
So you feel that...
The length of the Hasse diagram is at most k.
Yes, so you see, it's very easy exercise to solve. It's already solved in the bright student we have. And the bright professor, they don't say, because better they immediately they get the solution, but they... So second exercise. Stanley in his paper, in fact, to prove that gamma, the chromatic polynomial for lambda equal -1, was the number of cyclic orientation up to the side. He introduced this new condition. Right, so he defined a new polynomial, gamma with a bar on the, which is exactly the same condition as the chromatic polynomial, but you replace, instead of having the strict inequality, you have it may be equal. And then there is some few pages in this paper to show that this is the starting point of this proof, that this polynomial, new polynomial lambda, is in fact the value of the old one for minus lambda, up to the sign. So this was at the time, it's kind of duality between replacing, for example, in the binomial coefficient, this is a number of ways to choose k element over n. If you replace n by minus n, which give you up to the sign, give you this binomial coefficient, it's the same as replacing combination without repetition with combination with repetition. So you can repeat some letters, and then you get this coefficient, which comes from this one by replacing n in minus n. So the exercise, or maybe research level exercise, proves this with the Heaps philosophy. You feel that the level I am doing, maybe you can, instead of coloring the level with distinct color, maybe you can repeat the colors. Repeating the color, the lambda is going to be associated to this idea. Repeating means taking the value lambda to minus lambda. And repeating the color means you have this the strict inequality when you go from one level to another become equality. So I don't think it should be too much difficult to interpret again this in terms of heaps of pieces. Now there is another exercise, interesting exercise, is the following. Green and Zaslavsky in 1983, they were interested in the number of acyclic orientation with only one sink. A sink, or there's only one, there's only one maximal or minimal element in the acyclic orientation. So in terms of heaps, this means it's a pyramid or anti-pyramid when the minimum, there is only one minimal element or only one maximal. And they prove that the number of such acyclic orientation with only one sink is up to the sign, plus or minus, the linear term in the chromatic polynomial. And they prove this by connecting this to arrangement of hyperplane. Some people in the room are going to be happy. They love arrangement, hyperplane arrangement. And then these people in 2000, they give 3 of the proof. So the research exercise is try to prove this using heaps of pieces. Because the linear term is a chromatic polynomial, you have to take the derivative. And 1/6 means pyramid. Oh, derivative. I don't know if I don't know. Just I claim this to a research exercise. I don't know if it's easy or not, but try to give an interpretation in terms of heap, and if you do it, make a paper. All this because the Heaps theory is not very well known, so each time you use this to reprove some theorem, maybe this gives some new interesting proof, and from this class you can easily get some paper, if you need the paper. Okay, now, so I will take the second part of this class, it's much smaller. Second part will be about matching polynomial. That's the second part. So, any question on the chromatic coloring? No? So I will take, we have seen already in chapter 2c, we have defined the matching polynomial of a graph. We have seen the Chebyshev shape first and second kind, reciprocal of Fibonacci, Lucas. So the matching polynomial graph in general, this was a graph only reduced a segment or a circle, a cycle. So here is a graph and a matching, I just repeat, matching is a collection, a set of 2 by 2 disjoint edges, pairwise disjoint edges. So 2 edges does not share the same vertex. And you put a weight on the matching. The weight is -1 for each diamond, its edges, x for each isolated point. And the matching polynomial is the sum over all such matching of the weight of the matching. The weight is the product of everything you see in the picture, the product of the x, the product of the -1. So I can write the definition of the matching polynomial, m index g of x, is the sum of all matching of -1, the number of elements in the matching, number of edges, x power the number of isolated points in the matching. Isolated point means no edges are going through this vertex, which I can also write equivalently. It's minus sum of all matching, or -1 number of elements of matching, x power n, if n is the number of vertices of the graph, -2 twice the number of edges. Because this is a number of vertex which are not covered by an edge. And so the reciprocal of the matching polynomial, so you just have to replace x by 1 over x, and then remultiply. So in the weight means that each isolated point is replaced by a weight 1 over x, and then you remultiply by x power n to get a polynomial, and this gives you, so minus x2 for each edges, and 1 for each isolated point. And so I get the reciprocal polynomial is sigma over all matching. The weight is minus x2 for each edges, power the number of edges. And so this is a generative function, you see. Generative function for heaps of edges is the inverse of this matching. If you replace t by x to the square, it's you get the generative function for heaps of dimers over a graph. And the proposition, it was done by in chemistry, in physics. The proposition is an interesting proposition. It's that the zero of the matching polynomial, for any graph, the zero of the matching polynomial are real number. We have seen this for the Fibonacci and Lucas polynomial. So a reciprocal up to change of variable of the Chebyshev polynomial, and we know the zero of the Chebyshev with cosine. You can explicitly give the zero of the Chebyshev polynomial as a real number. So this is true for any graph. The matching polynomial are real number. And I'm going to prove this by using Heaps bijection. It's almost 100% time bijective proof. Yes, bijection not only can give identity, but can prove things like this. As soon as you reduce the problem to something well known about polynomial and a real number. So if G, in the case G is a tree, then the matching polynomial is equal to the characteristic polynomial. Because for a tree, the cycle, when you have the cycle, the matching polynomial on a tree, you have edges, and you can replace edges by a cycle of length 2. And if you take the characteristic polynomial of the tree, remember the formula for characteristic polynomial for this? It was, you have to take a trivial ellipse of cycle. You put x power here, the number of resulted points, and you take trivial ellipse of cycle. So any cycle on the trees is only loops or a cycle of length 2. And if I am not allowed to do loops on the tree, then I have only cycle of length 2. So in this big expansion of a determinant, as trivial ellipse of cycle, it's only restricted cycle of length 2. And if I have only cycle length 2, then this is a matching. See, so the matching polynomial is that look like a sub-polynomial of the characteristic polynomial. You delete all the cycle which have a length 1 or bigger, or strictly bigger than 2. You keep only cycle of length 2.
What is A here?
A is the adjacency matrix of the graph. Of the tree also. The tree as a graph. You take the adjacency matrix of the tree, and you get this polynomial will be the matching. And so I just translate, I adapt to Heaps a proof given by Godzil a long time ago. The proof of Godzil was introduce this tree-like path. So we go back to the exercise 3 of a certain chapter. Tree-like path is path which behave a little like a path on a tree. So a tree-like path, by definition, is now you take any graph, you take the bijection key, between any path are in bijection is a pair eta E, where eta is a self-avoiding walk, E is a heaps of a cycle, and a tree-like path, if and only if, all the cycle have length 2. See, there was an exercise. First exercise was a non-backtracking path, where you don't go back. You go from S to T, and then you go back on your step from T to S. This is a backtracking, and the exercise was, is it equivalent to say that the heaps have no cycle length 2? No, it's not equivalent. You can have a backtrack without cycle of length 2 in the heaps, and you can have cycle of length 2 in the heaps without a backtrack. It's not. But here it's all the path is like backtracking. Only way is going, and then you go back to get only cycle of length 2 on the bijection. So it's the example of a tree-like path. Of course, as a dig path, the projection of a dig path, when you move on this line, if you have an I, you go to I plus 1 or I minus 1. So the only cycle which will fall down on the heaps will be cycle of length 2, or the bilateral dig path, also the same, or more generally, path on a tree. When you take a path on a tree, if you take the bijection key with self-avoiding walk and a heap, then only cycle of length 2 will fall down on the fundamental bijection. So tree-like path on a graph. Here is an example of a tree-like path. See, you go like this. You go, see, so you are doing the self-avoiding walk, and in the loop erase process, you see, in the loop erase process, only loop erase are allowed. You go back on your step. See, you do this, for example. You go like this. So I told you it was like the story of the Petit Pousset in France, who was lost by his parents in the forest, and he put all this stone on the lattice, on the forest, so that so he goes there, and Petit Pousset would not go here, because he's making a cycle, and he's losing a lot of stone. So you go back on your step, you say you never step on your, so you keep your stone in your pocket, and don't do that, this and this, so you go back. And when your parent lost you in the big forest, then you can always go back to the origin, because all your paths in stone, you can return to the origin like this. You see, you look, so you are looking your house, but you are sure to go back to explore the whole graph like this. So this is a tree-like path, started with you and going back to you. So I can apply now again two of the three basic lemma, inversion lemma, and this bijection between path and pair of this should be eta and f. So let's take a path on a graph. The path starts with S, go back to S. S is the vertex of V, and I take the summation of tree-like paths starting from S, going back to S. So I apply these two basic lemma. So I have the inversion theorem, numerator divided by denominator, and the denominator is a matching polynomial. It's because it should be the sum of trivial leaps of cycle. The cycle have only length 2. And here the numerator is trivial leaps of cycle only length 2, which avoid the point S. So this is a matching of the graph G minus S. So I have this matching polynomial appearing as a denominator. Now the zero of the matching appear in both numerator and denominator as a pole of this rational fraction if the graph is finite. So now in chapter 3, slide 65, there was an exercise. So here is a solution of the exercise to construct. If you have any tree-like path for any graph, then there exists a tree such that the generating function of the path in the tree is going to be the same as the generating function of the path of the tree-like path in the graph. So I define a tree for any graph. You have a vertex S. I define a tree T next X of G. So the vertices of the tree are exactly the self-avoiding path of the graph. The root is the vertex S, the same as the vertex S in the graph. And here is the vertex of the tree. It's the whole self-avoiding walk, going from S0 to Sk. And you put an edge between two vertex inside the tree, if and only if eta prime is related like this with Sk plus 1 does not belong. It's still a self-avoiding walk. So I will put an edge between this vertex of the tree and this vertex of the tree. See, example, for this graph, we have seen the acyclic orientation of this graph, but here is a TS of G for S equal 1. So you have self-avoiding walk, you see. So, for example, if I go from 1 to 5. This is now I go 1, 5, 2 means I am going here. 1, 5, 2, 4. So if you take self-avoiding walk in the graph, you are going back down in the tree. At each step of your graph, you have different choice to go if you continue not going backward. So exactly the same choice in the tree. And when you go back in the tree-like path, making a cycle of length 2, then you go back in the same way in the tree. So you feel, maybe it's not formal proof, but you feel that the generating functions are the same. The behavior of the path in the graph is exactly reflect the behavior of the path in this big tree. And so I have the equality that both generating functions are the same. So this derivative function is this. You guessed already the end of the proof. This generating function is a matching polynomial for the tree, but we know that the matching polynomial of the tree is a characteristic polynomial. And this characteristic polynomial, the roots are real number because the zero of the characteristic polynomial is well known. It is the eigenvalue of the adjacency matrix, and the adjacency matrix is symmetric. So, classical theorem, the eigenvalue are real number. And so it's not totally finished, I should say, because maybe there will be a few problems when you put the equality between these two. So here, in the tree, all the zero above in here are real number. But here, there may be some cancellation. Maybe some zero non-real can cancel with a non-real zero here. So there are a few problems, but if you now, okay, allow me to do by recurrence. if it's true for any graph with n vertices, then it's true for any graph with n plus 1 vertices. Because if it's true for n, okay, this one has all real number, and below it's degree n plus 1. And if there was an imaginary root, then it would cancel with root here, which is, there is no imaginary root above. So if you allow me this slight induction, if you allow me to use this classical theorem, eigenvalue of characteristic polynomial are real number, then I get a proof of this beautiful theorem. And the zero in chemistry, in quantum chemistry, it's important. The zero of the characteristic polynomial when you are matching, especially for benzoid molecule, all these zero, they correspond to the level of energy in the molecule. So it's really important for chemists. In chemistry, there is a lot of things about zero of this matching polynomial for benzoid molecule with hexagon inside. And so this trip in chemistry and quantum give you the end of this chapter. Okay, thank you very much.